The news headlines of recent days says that Professor Martin Herrer of mathematics from the Imperial College has won $3 million on a prize on his work on mathematics. What is his work? So of course the news articles won't tell you what he actually worked on, so I went ahead and looked a little bit on his work, and it's pretty interesting to know what do professor of mathematics that won the biggest prize, what is his work about, or in other words, what do current mathematicians in the 21st century are working on? Is there anything left? So basically, I will sum up in general what his concepts are for you. I have no intention of understanding his formulas, I have no time for this, but the general concept is pretty straightforward, and we can all benefit from understanding what he's working on. So this is what Martin Herrer says. He says, if you look at random events, his work is on probability and random events. So he says, if you take a look at random events, then there are two main principles. The first principle is the symmetry, which means if you do a coin toss, the coin itself does not care. It does not give a damn about whether it's resulting with head or tails. So the symmetry here is that we either get a tail or head. Very straightforward, and I really like it. That like Nobel Prize level, he didn't win a Nobel Prize, but he won even a bigger prize. Nobel Prize level scientists are going back to the basics. I think we see this principle repeating again, that when you get to the top of the top of the top, you get back to the basic principles. What is the material built from? Are there atoms? Okay, so this is what he's doing. He says that when you toss a coin, then the coin itself does not care. This is not his idea, okay? But this is the symmetry principle in probability and in random events, okay? For you, it does matter. For you, it does matter whether the coin resulted with a head or a tail, okay? If you play a Russian roulette, it does matter if the coin is a bullet or not. But the gun, it does not care, okay? So, and this is what basically giving it the effect of randomness. The I don't care of the coin. So, and here's the main point. In addition to this symmetry principle, we have the universality principle. And the universality principle says that if you take an aggregation of such I don't care events, and you take a look at the whole picture, then you begin to see patterns. Okay? If you take a look at the stock market graph, yes, or even on a single specific stock, then each purchase and each sale of the stocks affect the price in a very short manner. But the whole graph of the stocks is made out of these lower level events. And while these lower level events, even in coin, are pure randomness with the symmetry rule, then the global picture is you can see an actual pattern. You can see a bell curve. If you take a mean of samples, and then you take the mean of these means, then it does not matter what was the underlying distribution, you will get a bell curve. And this what provides us with the ability to do hypothesis testing. Otherwise, everything is pure random. Okay, so he mentions these two rules, the symmetry and the universality, where you begin to see patterns, and he gives a few more examples, such as if you take a grain and you put it on a glass of water, and the water does not move, then you could see that grain is moving from one place to the other, and the water does not move. So Einstein also saw this in the beginning of the 20th century, and his assumption was that yes, while the water does not move and the grain move, we assume there are particles such as molecules. And remember that Einstein, in the era of Einstein, in the beginning of the 20th century, no one has proven, no one has saw molecules. It was only an assumption. It's pretty crazy. Like, it's from the time of Archimedes, I don't know how, until the time of Einstein, that nobody knew, including Einstein, nobody knew that there are actually molecules. Nobody has seen them. Nobody has proven it, actually. It was an assumption. Crazy. So Einstein, what he said is that the grain is moving because the molecules that we are assuming that they exist, right? We don't know that they exist. We assume that the molecule exists. We assume they move all the time because of heat. Okay, the heat is the velocity, is the moving of the particles, and so we, on the whole picture, we see the grain moves on the glass of water. So again, the symmetry principle is the random movement of the lower level molecules. The universality principle, the Gauss pattern, is the movement of the grain when we take a big zoom out and we look at this grain. Same thing with stocks. A single stock is having a lot of like lower level random events of purchase and sale, but when you look at the global picture, then the stock either rises or falls. Okay? Same thing with, he presents like in his papers, a game of Tetris. You have no idea what would be the next block. It's random. It's the symmetric principle. It's the I don't care which next block the game of Tetris, the Sony PlayStation is bringing you. But the whole picture, if you take a zoom out, amazingly, you would see an actual pattern, and the pattern would repeat itself. Like if you had a vacuum somewhere, an empty space, in the Tetris, you would continue like seeing it if you take a big zoom out. Now, what he says is that it's not enough to take like some zoom out, you have to take a very, very big zoom out. He actually shows that when you take some zoom out of the game of Tetris, then you don't really see this kind, you see a pattern, but you don't see the pattern that he is talking about. Okay, so we see this in almost any field. We see this with the noise. Okay, you have a wave, and you have some little noise on the wave. So Wiener was another professor of mathematics, and he investigated and came up with the first principles of noise cancellation. His student, the student of Wiener, was Bose. He continued this research, and this is the same Bose headphones that you're using. This is like, it's all related one to another. Bose was Wiener student investigating the noise cancellation, which is random events, which is the symmetry, which is the universality. And this is what, and now you're wearing these noise cancellation headphones of Bose, the student of Wiener, and this is what Warting Heiner is investigating. So we get this also with the noise. If you take a look at the plane of the sun, okay, so you see like black spots and white spots, so you see a pattern, right? In all the pictures that you see on TV of the sun, then you see some patterns. But if you take a closer look, you won't really see these patterns. So you take a big zoom out, you go to the Earth, look at the sun, you see the patterns. So what he's saying is that this universality, except for the Gauss, which we really know very well, the Gauss pattern and the bell-shaped pattern. We know this very well. It's well investigated. You study it in basic courses, like in the first statistics course in university. You study this. This is the basics, okay? But then the universality or the patterns, which are not Gauss, which are not bell-shaped, are much less investigated. And this is what he tried to investigate. He tries to investigate, and this is his very great work. For this, he got the $3 million. So he investigated this zoom out of small random events, and his method was, okay, we know Gauss very good. We know the bell shape very good. Nobody knows the other shapes good of the randomness and the external randomness. So what I'm going to do is I'm going to take this bell-shaped or this Gauss, I'm going to tweak it and to come up with a new model, and I'm going to prove it. So this is his paper. I'm going to take the well-known shapes. I'm going to, next step, tweak them so that I can come up with a model for the other Tetris, stock market, heat, random shapes. Those shapes are pure random, but when you take the zoom out, you see some pattern. And I will prove that I could take this step, with a tweak from the Gauss and the bell shape into the outer layers. And in the last 10 years, he was working on such a general theory. The general theory was, I take these low-level random events, I run them like in a simulation, I tweak some parameters, at first you think it didn't affect anything, like I tweak like which shapes are coming, or in the Tetris, I tweak something very small, like if I tweak a parameter like from 1 to 2, then it's a great tweak, but I tweak 0.001, you don't see any effect. You take a zoom out, you don't see any effect. You take a big zoom out, like from the Earth to the Sun, and you do see this effect. So this is his general theory about the universality and for the prediction of large-scale behavior. Like you take a company, you have a lot of software developers, this is the random events on the lower level, but you need a big picture. The big picture, which is the system of systems. And how the big picture behaves, how the system of systems behave, this is like less random. But if you apply his formulas and take the parameters, then you can come up with some kind of prediction of this large-scale event. So this does not mean you would be able to predict the stock market or how a company behaves, but this means you can apply some shapes, and given some parameters, you can come up with what are the possible shapes to come, what is the possible vacuums that you would see, and what are the possible shapes with the system of systems. I think this gave us, and myself, a very good glance into what current academia mathematicians are discovering and working on in the recent years. I think it's, I'm actually very happy to see that the state of the art and the latest math is coming back to the principles. This is a repeating theme. I really like this. It's very enjoyable. I think that they're getting back to the first principles, like do molecule exist? And from these very first principles of symmetry and universality, they come up with their genius minds and brains with general theories that describe these very complex behaviors. So this was a very short description to 160 pages paper. So I think this was very interesting and very optimistic, and I hope you enjoyed this, and I will see you next time.